The first new concept we're going to look at is intermolecular forces, and how these forces will affect when matter will change state. But before we get started on intermolecular forces, we need to recall some concepts that we have learned before, and then expand on them a bit. First, let's review the ideal gas law, and expand it a bit with the kinetic molecular theory of gases. Ideal gas law says that the pressure times the volume equals the moles of gas times the gas constant, and the temperature in Kelvin. This law is valuable to approximate the behavior of gases. However, it is not a good description of all gases. The kinetic molecular theory describes the conditions under which gas will behave in an ideal way. First, the gas particles in the container are in constant random motion. Second, the container occupied by the gas particles must be mostly empty space. This means that the volume of gas particles themselves do not contribute significantly to the volume. So the volume of the container is equal to the volume of gas. Third, the gas particles collide elastically with the walls of the container and each other. They do not experience attractive or repulsive forces. Fourth, the pressure the gas is exerting on the container is entirely due to the force of the collisions of the gas particles with the wall of the container. And finally, the average kinetic energy of the gas particles is proportional to the temperature. Mathematically, that looks like this. The yellow side is the mathematical expression for kinetic energy, and the green side represents the average kinetic energy of the collection of gas particles. From these conditions, we can draw some conclusions about how close to ideal a specific gas condition might be. There are three simplified rules that we can use to do a quick and dirty estimate of the ideal nature of a particular system. Gases are closest to ideal when 1. The volume is large and the pressure is small. 2. When the temperature is large, which increases elasticity of the collisions. And 3. When the gas particles are small and there are not a lot of them. Let's give this a try. Which of these gas conditions are more ideal? 1 mole of xenon at 5 atmospheres and 200 Kelvin, or 100 moles of xenon at 5 atmospheres and 200 Kelvin? The key to the answer is the pressure and temperature are the same, so only difference lies in the amount of gas. Number 3 says the less gas particles there are, the more ideal a gas is. Thus, 1 mole of xenon is more ideal than 100 moles of xenon. Review pages 6 and 7 in your workbook and work through the problems on page 7. Next, we already know that there are 3 basic states of matter. Physicists and chemists have discovered, or created, more than just 3. But these 3 are the types of matter we encounter most often in our daily lives. They are solid, liquid, and gas. We can define these states based on how they interact with their container. A solid does not change shape based on the shape of the container. It also cannot be compressed nor flow within the container. It holds its own shape. A liquid will take the shape of part of the container, but it will not expand to fill the whole container. It can flow around readily, but it is still virtually incompressible. When things try to diffuse through a liquid, that process happens slowly. A gas, on the other hand, will completely expand to fill its container. This means that it is also easy to compress, and that diffusion within a gas happens rapidly. Work through page 8 in your workbook. We need to review molecular shapes and polarity. Remember electronegativity? Electronegativity is a property of atoms that is related to Z effective. The nucleus of an atom is surrounded by electrons that occupy energy shells. Energy shells are designated by quantum numbers, where n represents the basic energy level of the orbital. The core electrons in an atom shield the outer electrons from feeling the full force of the positive charges in the nucleus. These core electrons represent the previous noble gas configuration. This is easy to see when we write the electron configuration using the noble gas abbreviation. The more positive force that is felt by the outer electrons, the higher the Z effective and the higher electronegativity. Z effective and electronegativity generally increase when we go left to right in a row and decrease as we go down. Polarity in a molecule is created when 2 bonded atoms have significantly different electronegativities. The higher electronegative atom will tend to keep the electrons closer to it. This creates tiny positive and negative charges on the atoms, with the electronegative atom having a slight negative charge and the less electronegative atom having a slight positive charge. This is called a dipole, like the two sides of a magnet. Molecules that have a polar bond are also polar, unless, like CO2, the polarity in opposite directions cancels itself out. This makes CO2 nonpolar. Thus, the polarity is affected by the presence of polar bonds and the three-dimensional shape of the molecule. To see the polarity of a molecule, it is important to review the different shapes of molecules based on their bonds. Here's a chart of all the possible geometries of molecules. Remember that the geometries are related to the hybridization of the orbitals. Let's take a look at a molecule and determine its shape and polarity. Phosphorus trichloride. What is the geometry of this molecule? Let's create a Lewis structure for it. Great. Now we can count the number of domains around it. There are 4, and 3 of those are bonding domains. Thus, phosphorus trichloride is trigonal pyramidal. Also, chlorine is more electronegative than phosphorus and pulls the electrons away from it to make these 3 polar bonds. Because only 3 of the 4 domains are electronegative, with the 4th being a simple lone electron pair, the electrons are not evenly pulled and the molecule is polar. Review pages 9 and 10 in your workbook and try the problems on page 11. We should be comfortable with Lewis structures. However, these are not the only way to represent molecules. Let's look at a few different ways to represent molecules that will be helpful later and can save time compared to Lewis structures. If we start with the Lewis structure of propane, we can see how that relates to the condensed formula of C3H8. However, just writing C3H8 doesn't tell us much about the way the molecule is arranged. We can also write it like this, which tells us more about how the molecule is bonded together. Organic molecules come in a wide variety of shapes and structures. We can look at the molecule diethyl ether. Here the oxygen is the center of the backbone. We can write this in a condensed form, C4H10O. But again, this isn't very helpful. We can also write it like this, which gives us more structural information. What about a molecule that looks like this? The condensed formula is C4H11N. However, this nitrogen group is attached to the second carbon. We can use parentheses to write this as this. Review page 12 in your workbook and try the problems at the bottom of the page. For organic compounds, we can use line structures. A line structure is like a stripped-down Lewis structure that only explicitly denotes atoms other than carbon and hydrogen. Carbon and hydrogen atoms are implied by the basic skeletal structure. Here's our Lewis structure for propane, and here is the line structure for it. We can see that each tip or bend in the line represents a carbon atom, and the hydrogens are implied to fill all the unwritten bonds. Because carbon is sp3 hybridized when surrounded by only single bonds, we can assume hydrogens will fill in all the missing spaces. If a molecule has other atoms, such as oxygen, we will include that as well as hydrogen, attached to it directly. Nitrogen is the same way. Remember that bonds in organic molecules fill up using the honk rules. Double and triple bonds are represented by 2 and 3 lines, respectively. Review page 13 in your workbook and try the problems at the bottom of the page. In the next lecture, we will take a look at intermolecular forces and how they dictate the behavior of substances and compounds.